Today's question is, if A is a square matrix of order 3 such that determinant of A that is equal to 3 and determinant of adjoint of minus 4, adjoint of minus 3, adjoint of 3, adjoint of 2A inverse that is equal to 2 raised to the power of m times 3 raised to the power of n. Then we need to find m plus 2n value. This is a given question. So let's see how to solve it. So what they given information, if A is a matrix of order 3, the order of the matrix is 3, that means n value is 3. Determinant of A, the value is 3. This whole expression that is equal to 2 raised to the power of m times 3 raised to the power of n. If you convert this whole expression in terms of a 2 raised to the power of something times 3 raised to the power of something, then that is equal to 2 raised to the power of m times 3 raised to the power of n. When bases are same, we can equate the powers. So using that property, we can take m and n values. Let's see how to convert this whole expression in terms of a 2 raised to the power of something times 3 raised to the power of something. Let's see how to do it. To find the m and n values, we need to recall two most important formulas. Those two formulas we are going to be used here each and every time. So you have to learn those two formulas. The first one is determinant of adjoint of A. The formula is determinant of A whole raised to the power of n minus 1. Here we have a. Instead of A, if we have a Ka, the right hand side also we have to write, here also we have to write determinant of Ka whole raised to the power of n minus 1. This is the first formula. And the second most important formula is determinant of Ka. The formula is k raised to the power of n, determinant of A. Here n is nothing but order of the given matrix. So these two formulas we are going to use frequently. We are also using one more property, that is determinant of A inverse. We know that A inverse is nothing but 1 over A, isn't it? So this we can write it as 1 over determinant of A. Determinant of A inverse, we can write it as 1 over determinant of A. Using these two properties, I am going to convert the left hand, the whole expression in terms of 2 raised to the power of m times 3 raised to the power of n. So let's see how to do it. Let's take this only the left hand expression. It is in the form of the first formula, isn't it? See, first we have determinant of adjoint we have, then we have minus 4 times this whole expression. If you consider this whole expression as capital A, so then it is in the form of determinant adjoint of minus 4a, isn't it? So it is same like as our first property, which is determinant of adjoint Ka equal to determinant of Ka whole raised to the power of n minus 1. So let's use this one. Here K is nothing but minus 4. So let's write this. Determinant of minus 4, A is nothing but this whole expression, isn't it? So let's write that. Whole raised to the power of n minus 1. Our given matrix, they said it is order of 3. That means n value is 3. So here n value is 3. So if you write here n minus 1, which is 3 minus 1, which is 2. Now observe this one. I am going to write this whole expression here. Now observe here, it is in the form of determinant of this minus 4 is a constant. So we can write this as k, and this whole expression we write it as a. So it is in the form of our second property, which is determinant of Ka, that is equal to k raised to the power of n times determinant of A. So use that second property. So we can write this as k raised to the power of n determinant of A. This expression we can write it as k raised to the power of n. K is nothing but minus 4. Here n value is 3. In our expression we have a whole raised to the power of 2. So we have to do square on both sides. So then the formula turned into k raised to the power of 2n times determinant of A whole raised to the power of 2. So you have to write in terms of this. What is our k value? Minus 4. So just write minus 4 whole raised to the power of 2 times, what is n? N is nothing but 3. So just write 3. A determinant of A is nothing but this whole expression. So just write only this whole expression. Whole raised to the power of 2. 2 times 3, which is nothing but 6. So just write whole raised to the power of 6. In the power we have an even number, so the negative value change into positive. So here minus 4 whole raised to the power of 6. We can write it as 4 raised to the power of 6. Observe only this expression. It is in the form of our first formula, determinant of adjoint of KA. So what is the formula for this? Determinant of KA whole raised to the power of n minus 1. So just write that. Here K is nothing but minus 3. So you just write minus 3. This is our A. So you just write adjoint of 3 adjoint of 2A inverse whole raised to the power of n minus 1. Here we have a power 2. Both sides in the power you have to take 2. So here also you have to take power 2. The n value is 3. So here you have to write 3. So 3 minus 1, which is 2. So just take only 2. Now here power 2 and whole power 2. It becomes whole power 4. Now observe here, it is in the form of determinant of K times A. Isn't it? So that is our second formula. See here, determinant of Ka. So the formula is K raised to the power of n times determinant of A. K raised to the power of n times determinant of A. Here we have a power 4. So you have to take that power 4 on both sides. So this right hand side turns into K raised to the power of 4n. Then determinant of A whole raised to the power of 4. So here K is nothing but minus 3. So you have to write minus 3 4 raised to the power of n value is 3. So then times determinant of whole raised to the power of 4. So you have to write like this one. So here 4 times 3 is nothing but 12. So minus 3 whole raised to the power of 12. So you have to write directly here. Minus 3 whole raised to the power of 12. Then determinant of A is nothing but this whole expression. So you just write adjoint of 3 adjoint of 2A inverse whole raised to the power of 4. So now observe again. Again this one, it is in the form of our first formula. What is our first formula? Determinant of adjoint of Ka, that is equal to determinant of Ka whole raised to the power of n minus 1. And here we have a power 4. You just take power 4 on both sides. Determinant of Ka n minus 1. N is nothing but 3. 3 minus 1, which is 2 whole raised to the power of 4. So this power 2 and whole power 4, it becomes 2 times 4, which is 8. So after applying the first property for this determinant, we got this, which is determinant of Ka. Here K is nothing but 3. So 3, A is nothing but this expression. Then whole raised to the power of 8. At front we have 4 raised to the power of 6. And here minus 3 whole raised to the power of 12. 12 is an even number. So automatically this negative value turns into a positive. Then become 3 raised to the power of 12. Now observe again. This expression, it is in the form of determinant of K times A. So now let's take the second property. Determinant of Ka, that is equal to K raised to the power of n times determinant of A. Here we have a power 8. So let's take power 8 here. Here K is nothing but 3. So 3 raised to the power of, and n also we know that it is the order of the matrix, which is 3. Determinant of A whole raised to the power of 8. When you open the bracket, it becomes 3 raised to the power of 3 times 8, which is 24, times determinant of A raised to the power of 8. So you had to write here 3 raised to the power of 24, determinant of A whole raised to the power of 8. At starting we have these two terms, which is 4 raised to the power of 6 times 3 raised to the power of 12. Here A is nothing but this whole expression, isn't it? So you have to write that whole expression, which is adjoint of 2A inverse. Now observe here. Here bases are same. When bases are same, we can add the powers. So we can add these 12 and 24. So after adding, then we are going to get 3 raised to the power of 36. Here we have 4 raised to the power of 6. This 4 we can write it as 2 raised to the power of 2 whole raised to the power of 6. So 2 raised to the power of 2 whole raised to the power of 6, it turns into 2 raised to the power of 12. Now observe this expression. It is in the form of our first property. So what is our first formula? Determinant of adjoint of Ka, that is equal to determinant of Ka whole raised to the power of n minus 1. So here n is nothing but 3. 3 minus 1, which is 2. And here we have a power 8. So let's take power 8 on both sides. So then become in the determinant of Ka whole raised to the power of 2 and whole raised to the power of 8, it turns into whole raised to the power of 16. So this expression we can write it as K is nothing but 2. So you can write as determinant of 2 A inverse whole raised to the power of 16. What do you call the third formula? So what is our third formula? Determinant of A inverse that is equal to 1 over determinant of A. Instead of A inverse, we have a 2A inverse. So that's why you have to take 2 here. If you take 2 here, then here also 2 comes. In the power we have a 16. So let's take 16 on both sides. So that means determinant of 2A inverse whole raised to the power of 16, we can write it as 1 over determinant of 2A whole raised to the power of 16. Determinant 2A, it is in the form of determinant of Ka. This is our second formula. So we can write it as K raised to the power of n times determinant of A. So we can write this as 2 raised to the power of n. N is nothing but 3 here times determinant of A. We have a power 16. So let's take power 16 on both sides. So then become 2 raised to the power of 3 times 16, which is 48 times determinant of A whole raised to the power of 16. So the denominator value we can write it as 2 raised to the power of 48 times determinant of A whole raised to the power of 16. Now determinant of A. So what is the determinant of A value? Determinant of A, the value is 3. So let's take that. Determinant of A, the value is 3. So now the denominator values, you just take it to numerator. Then 2 raised to the power of 48, it turns into 2 raised to the power of minus 48. 3 raised to the power of 16, it turns into 3 raised to the power of minus 16. Observe this 2 raised to the power of 12, 2 raised to the power of minus 48. Here bases are same. When bases are same, we can add the powers. For the 3 also, when bases are same, we can add the powers. 2 raised to the power of 12 minus 48. 12 minus 48, which gives minus 36. 36 minus 16, which gives 20. After simplifying this whole expression, we got this 2 raised to the power of minus 36 times 3 raised to the power of 20. So this whole expression, after doing some simplifications, we got this as 2 raised to the power of minus 36 times 3 raised to the power of 20. So that is equal to what we have on right hand side. We have 2 raised to the power of m times 3 raised to the power of n. When bases are same, we can equate the powers. So from that, we can say that m value is minus 36, then n value is 20. Our goal is to find m plus 2n value, isn't it? So what is m value? Minus 36 plus 2 times, what is the n value? 20. So 2 times 20, which gives 40, minus 36 plus 40, which gives 4. So finally m plus 2n, the value is 4. That's it.